Okay, let's go. Welcome back, Big Data Con. Here in the next talk, I'm Jörg from Trustbit, and I'm very honored to have Federico with us today on the stage. One clarification at the beginning about the title of this session. The title of today's session of Federico is Mainframe and Serverless Integration: How to Liberate the Data and Stay Competitive in the New World. So as you have written in the description, it's all about serverless coming from a mainframe. Federico has several years of experience in the financial sector too. I have experience with different cloud provider like AWS, like Azure, and so on, you name it. And now it's time for you, Federico, to tell us a little bit how we can move from a mainframe time into, and use proper AWS, modern technology, modern services, and especially going serverless. What does it mean? The stage is yours. Please share your screen, Federico.
Perfect. Thank you. Thank you. Let me just share my screen. There you go. Share screen. And we should be fine. Hopefully you should be able to see my screen coming up now. Yes, there it is. Okay. So we can start the session. Let me start my counter as well. So first of all, welcome everybody to my talk. My name is Federico and I work at Contino. So Contino is a global DevOps and cloud transformation company. We help large regulated enterprises moving from on-premises to cloud, building cloud architectures, reviewing their operating systems, their operating models as well, the way in which a company uses cloud. I'm Contino's VP of Engineering for EMEA in the UK, where I'm based in London. I'm responsible for the technical strategy of the company, the engineering resources, and I help as well on the accounts. Before Contino, I was at Curve and at Funambo, so I've always been in technical roles throughout my career. This talk really stems from our experience working with large regulated enterprises moving from a mainframe onto cloud and how they can use that. Because you have to realize that all these large payment providers now at our crossroads, they have been building their systems, the mainframe systems, for reliability. They haven't been building their system for feature speed, for velocity. They're building everything in a way that is secure, stable, that can be used by a large number of users, scalable as well if you want. But they haven't been building anything to be really fast at building new features. Their systems are not built for that. So what happens though is that we have all this, incumbent is challenged by startups, smaller startups, nimble startups, Monzo and Starling in the UK, and 26 in Europe, that are just competing really, really fast, and they can evolve and offer very advanced features. And so banks are effectively, they have access to way larger data sets. They have a data gold mine they could use to offer new features, but they can extract the data. They can work with the data because data is held in the mainframe. It's held in these very old systems where they've been working with data for the past 15, 10, 20 years, and they cannot extract the data. So all these new features that insights on user spending, user profiles, user behavior, looking at also fraud detection, live machine learning fraud detection, they're really, really hard for them. So payment providers have realized they need to evolve. This is not news in the industry. This has been done for the past 4 or 5 years, and even more probably. We've seen at this point large institutions trying to do this. But the idea here is that we're starting to stream data coming from the mainframe and using cloud to liberate the data. The technical solution really here is to replicate data coming into the mainframe. So every time a user makes a transaction, a financial transaction, this user will make a transaction and send data onto the main, and data will arrive in the mainframe. From the mainframe will move onto cloud and be streamed onto cloud. And so you start breaking down the mainframe silo and having multiple copies of the data replicated across the different cloud providers, across different services in the cloud. You're streaming data, and when the data lands in the cloud, you can liberate, you can make it available for utilization by others as well. So your data scientists right now are not constrained by having to query data stored in the mainframe, having to enter that queue. you can enable your data scientist to have access to copies of the data, to have access to different databases, different systems, different data lakes, different data warehouses, where they can then use the data and provide insights, generate insights. They can not only do that, they can turn data into knowledge. This is the key thing. So they can then offer the same type of services. So banks can offer the same type of services to their clients that then smaller startups can offer by exiting the mainframe and using cloud to do it. So let's review the architecture. As I told you, this is non-news in the industry. If you're looking at this, I continue, I've been working with a number of clients building this. There's even a talk from HSBC at AWS reInvent from 2018. So what HSBC was doing is basically in this talk is doing something very similar to what we're talking about, streaming data from the mainframe onto cloud. But they were leveraging EC2 compute instances, VMs, we're instead using serverless. And throughout this example, we'll be using also AWS. You will see which is a cloud provider focused on this example. So as I said, we're starting with streaming the data from on-premises to the mainframe. We're then having 2 points in time, which we're making use of the data. One point in time is the real time. Because we have real-time needs. So data from the mainframe goes to cloud, and then from transactional purposes, we can update the data there. We can send notifications to our users live. We can make transactional use of the data in the cloud, or we can store the data for further consumption in the cloud and enable exploitation of the data through data analytics. So we can build data lakes, and we can have multiple data scientists generating analytics on the data in data lake and providing advanced services to the customers. So we have 2 utilization points, 2 vantage points where we're using data in the cloud. Step 1, looking at the architecture, extremely simplified, as you can imagine. In our example, we can say that we have some data in the mainframe that goes to AWS, leveraging AWS Kinesis, which is a standard data streaming service. From Kinesis, we're having Lambda functions, AWS Lambda function consuming the data and storing the data into DynamoDB. DynamoDB is a NoSQL engine where data is immediately available to then be consumed by an API gateway and a Lambda function with it. Standard serverless architecture. So I'm not going to enter too much of details of serverless here. I expect the audience to have some level of knowledge about serverless already. But you can see that all the services are auto-scaling. They're reliable. You don't need to worry about maintenance of the service, nor to do anything about them. Services are ready for use. And then when a user comes in, for example, a user needs to fetch their list of transactions from the mobile application or from their bank website. What they do, they open the website, and then behind the scenes, the website goes, and rather than reading data from the mainframe, their backend systems, they read data from AWS. This is the change. The change is that we're creating a copy of the data set from the mainframe, streaming updates onto AWS. We will go through a number of different deep dives, technical deep dives right now onto the core AWS services. We're going to see a few of them. I'm not going to dwell too much into those right now, but I just want to highlight to you that we have a number of services in this case, and some of them are data focused. So we're starting to see Elasticsearch, RDS, DynamoDB as well. All these services, data focused services that are required that we use to store copies of the data and optimize the use case. In other words, the takeaway, if you want, the talk really is to say that rather than moving from a place where we have one data store that serves both transactional and analytics use cases, we move to a set of variety of data stores, fully serverless, all of them, without operational needs, that enable more advanced utilization of the data. Let's see, so we're entering a bit more complexity here. So we're seeing that the architecture is not as simple anymore. So we're seeing that we're now focusing on, as I told you before, on the transactional use case, we're focusing on speed, getting availability, getting speed there, or we're focusing on storing the data. You see at the bottom as well, the data lake. So what I was telling you before, we see at the very bottom of the slide, the S3 buckets where data lake is stored, where data is, and we can see that this is the buckets that will enable then in a moment our data scientist, the company data scientist, to read and see how many transactions has a user performed, how many transactions have our user performed in the UK, how many of our users are going to coffee shop, how many of our users need this or that other service. It's worth mentioning as well that as most banks, data comes in a bank in a variety of ways. This is not on, you cannot simply stream data to cloud from the mainframe. Sometimes you have to accept in cloud batches of data the mainframe sends. Instead of sending you a small piece of information with one financial transaction, the mainframe sends you big XML, big CSV file with a lot of information and transactions. And you need to be able to process that. We do that in our example using S3. So we load the file onto S3 and the mainframe loads it onto S3, sometimes via an SFTP server. And then from S3, we trigger a Lambda function that processes the file, converts the file into a set of small messages that then are processed by the Lambda function. We're breaking down the file, trying to stay serverless. Very important. We can see that sometimes in the architecture example, we can see, I wanted to give some ideas of how big the system is. The system is really ends up being a serverless microservice architecture with a lot of Lambda functions, but also Fargate containers. Fargate containers, which is a technology to host and run containers, very similar to Kubernetes, but simplified effectively. Fargate containers enable us to overcome the limitations of serverless. When we have Lambda functions that need to run for more than 15 minutes, we start going serverless. We start using Fargate. When we have multiple teams that need to operate, we create multiple accounts. When we have multiple microservices as well. And microservices is very important, our focus of our work, going through different boundaries. Let's just now take a moment at some of the architectural highlights of the system, because as I was telling you before, when I break down the source, the golden source that we have in the mainframe where everybody on the bank is going to, and we're breaking it down into multiple data sources, the first concern of everybody spoken with is ensuring correctness. The bank wants to make sure that if you're sending the data in multiple places, the data is correct in all these places, because obviously the experience can be really bad. As a user, if you're fetching data through the mobile application of the bank or the website of the bank, and you're ending up on a copy of the data in DynamoDB that is not in sync with the mainframe or as issues, you may be shown wrong financial data. So you really want to be really careful about this and ensuring correctness. How do we do it? Well, first one, we need to define what correctness is. And this is a small slide just to say that we need to define the acceptable levels of service. We need not to say we want all our data to be correct. We need to be really precise, defining the SLOs, saying, I want 99% of the GET API calls for the transaction over a minute to return the most up-to-date data in 100 milliseconds. It's really important to define the NFRs as a step one. And then we ended up creating an end-to-end testing system. From multiple vantage points, we verify the correctness, the formal correctness of the systems, adopting an end-user perspective. So we have multiple probes that we send into the system, and they send synthetic transactions, and then they check, as if they were a user, what is the result. By doing this, by injecting transaction into the mainframe and having the transaction streamed over and checked into multiple vantage points, you can make sure that you're doing the right thing. This is a bespoke system that was built just because there is a lot of complexity around the transaction logic itself to verify multiple things. It's built on Java and is deployed as part of our systems as well. We then have a couple of transaction reconciliation systems. These are traditionally built in banks. There is an in-band and out-of-band transaction reconciliation system. These systems are used for streaming data. So in one hand, we have the mainframe doing replies, and we have idempotency tags throughout the system that check, okay, so if a transaction comes in twice or does not come, we have monitoring, and we can process the same transaction multiple times without having any negative effect. It's a key point because our distributed systems using Lambda and Kinesis only has at least once guarantees. So each message can be processed twice, but obviously we don't want to book the same amount twice to the same user, clearly. So we have the stacks in place. We also have, as most banks do, an out-of-band, recommend having an out-of-band system, which is a system that says, okay, because you're sending me streaming data all the times, why don't you instead send me a batch of the streaming data you sent me in the last hour, in the past day, and I check the batch to tell you if I'm up to date. This out-of-band system is a way in which the mainframe itself, or a system connected to the mainframe, sends to AWS list of transactions that were processed over the past 24 hours to ensure that the transactions are stored in all the downstream systems in the cloud. Super important, and follows a different path from the usual one. We end up having what we call a high watermark. So we understand exactly where the systems are in sync up to. Maybe they're in sync up to 11:56, 13:56 of the 29th of September, at the specific point in time. They are in sync. And then they can get out of sync, but at least we know where we are up to date. And then we have a number of, this is a complex system that has manual and automated steps as well to ensure correctness around this. We see this in a small slide, how it works. It's a fairly complex system that, as I was telling you, uses multiple technology. So this is where, when we have to process this big batch file, we start using we start using S3 and we start using Fargate, because we want to be able to break the 15 minutes limitation that Lambda functions currently have. Another interesting feature that we're offering, as I was telling you before, we're offering full text search. So if your bank users want to search text in their transactions list, so for example, their users want to search for all the transactions they processed, all these Starbucks transactions they made. So they search for star in their mobile application. Well, this before used to go to the mainframe and be converted into a complex query that has this full text capabilities in the mainframe, but it's a slow query. It takes a while, so it's very hard and there are significant constraints that get put on the query itself. So you cannot, if you're doing full text search, you cannot search more than a month. You cannot search for more than a couple of days. It's very important for you to do that. Instead, we want to overcome those limitations on the mainframe, and we're starting to do full text search using a dedicated database. We're not using Dynamo anymore for full text search because Dynamo is not suited for this. Dynamo doesn't let you do this. We're using the standard full text search database out there. We're using Elasticsearch. AWS offers a managed Elasticsearch instance that allows you to store the data and query data from Elasticsearch. You can see in the example here that the game doesn't change that much. So users or backend systems go to the API gateway. From the API gateway, Lambda functions are triggered. Lambda function, instead of reading Dynamo or instead of reading a SQL database, read Elasticsearch. And you can see sometimes that we start having multiple databases as well. We have Postgres in there as well, where the Lambda function sometimes reads from Postgres and integrates data that comes from Elasticsearch. I'm not a huge fan of having outside database data integration in memory in the Lambda functions. But in this case, it makes sense if you have just a reference data set in Postgres, just easy to manage. So we enable full text as a search in a number of places by using a different database. And then we're talking about data lake integration. So once again, we now want to enable our data scientists to leverage data in cloud. How do they do this? The scientists can easily do this by leveraging the data lake. So they're not going to go back and query again DynamoDB. They're going back and querying the data lake. They're querying copy of the data in S3. Copy of the data, how does it get to S3? Data arrives in Kinesis, and then we're using Kinesis Firehose, AWS native service, to send the data in S3, and then we do some enrichment, some cleaning of the data. The takeaway is data scientists do not query DynamoDB for data. The scientists query a larger data set stored in S3, and they can do what they want. We're having some complex, well, semi-complex, but standard way of doing data lakes as well, where we have a data catalog of the data that enables the Hive meta catalog through AWS Glue data catalog, which is a data catalog is a collection of tables and columns and explains where data is stored effectively. And then data scientists can use the tool they want, from QuickSight to EMR to Athena as well, to query then the data. So we don't impose the technology on data scientists. We tell the scientists, we're realizing the separation of storage and compute. We're offering you storage, bring compute. We're using, in other words, as well, the system to enable further online transaction systems, the event source. So if you're a data scientist, you go to S3 and you get the data. If you're a technologist, if you're a data developer, and you want to check each transaction, whether they're fraudulent or not, if you want to check each transaction, whether they want to send a notification to your user on each transaction, you can use the event source. As a system, every time a transaction comes in from Kinesis, you send the transaction to an event source, and you make it available for others to consume as well. So we're seeing, in other words, a variety of use cases, from full text search to analytics to event source, which enables further microservices and systems external to the transaction processing system here to consume the data. We're enabling this by spreading data in a number of places. We're enabling this, in other words, by exiting the mainframe, which otherwise would be a significant constraint. I'm going to spend a few minutes now jumping onto serverless patterns. So we'll be seeing how where we can build serverless patterns, which strategies we've used to build our serverless systems. This section requires some working knowledge of serverless, so I won't be explaining all the details for this, but I hope you'll be able to follow along as well. First step that you want to do in a system like this, use a circuit breaker. Circuit breaker enables you to smoothly transition. It's a technology that we're using on premises, in fact, that says, if AWS is not available, redirect a user request onto the mainframe back. So in order to smoothly transition from one system to the other and to provide a fallback, we're using a circuit breaker system. Now, we use it as well in other places, but I think the most relevant use case is to protect user experience, such as, because you are now having multiple systems in the distributed systems, you want to create a circuit breaker that can send requests from users back to the mainframe if one database in the cloud is not available, if the API gateway is not available. And as usual, when building a serverless system, we need to be careful in terms of patterns, like controlling scaling, which is super important. So the historical problem with Lambda, with serverless technologies, has been a cold start problem. I'm sure most of you will know about. In a case like this, where we want to have live transaction processing and we want to stay within 100 milliseconds, 50 milliseconds, we want to stay really, really fast, we can't afford these cold start problems. So what do? We use provision concurrency to avoid this, which is a technology enabled by AWS that basically, it's a bit brutal to say, but keeps Lambda warm that can be used to serve requests without having cold start problems. We will see that, in fact, the effects on the tail latency of the cold start problems was bigger by selecting the right batch size on Kinesis rather than selecting the concurrent provision concurrency, but still is a very useful feature. And then we are monitoring in our serverless systems also the impact on the downstream systems. So we're seeing in this impact, we want to make sure that when we're impacting these downstream systems, because we have Lambda functions that can potentially call RDS databases, Postgres databases. Well, if I have 1 million users calling API gateway at the same time, they will spin up 1 million Lambda functions that will open 1 million connections back to RDS. RDS will quickly exhaust the connection pool available and say, I cannot host any more connections. Max connection has been reached. So we have to, because the RDS doesn't scale as much as Lambda does, or in the same way, I guess. Lambda, I can open 1 million connections to Dynamo, but I cannot open 1 million connections to RDS. So I have to protect my downstream systems. We're using a few techniques in this. One commonly used technique is to use a message queuing system, in which you're basically creating a message in a queue, and then you're processing the queue and opening connections onto RDS. And by protecting setting the concurrent executions, you can prevent more than X Lambda functions to opening to RDS, connection to RDS. This can be used, but is far from ideal because it introduces a significant latency and also is not as easy to use in an API gateway. More modern solution, standard solution, is a connection pooler. They've existed for 20 years, connection poolers. In AWS world, we have RDS proxy, which is a solution that allows us to keep 4, 5, 10, 20, 50, 100 connections open to RDS itself, to Postgres itself, and then all the Lambda functions connect to the pooler, which acts as a proxy and limits the number of concurrent connections. Very important, as well as the dead letter queue pattern. So we're living in a at least once world. We're living in a world where we're sending a number, millions and millions of messages at the same time. Some of them will fail. The risk here is that if you have 1 million concurrent transactions per day, you can have a 1 in a million events happening all the times. So we enable item policy tags, but we also may have some transactions that for some reason cannot be processed. This is usually solved by using a dead letter queue system in which you're postponing the processing of the transactions. In our case, because of the correctness requirements, we also have monitoring, alerting on this, but it's a commonly used pattern. What I would recommend you doing in this case is that because you're processing micro batches of transactions in the system, choosing the right setting on kinesis can have a significant impact on you. So make sure to use, in other words, bisect on failure, in a way that your batch gets smaller and smaller all the times, 10, 5, 2.5, 1, and you end up not processing only that one transaction that crashes the system. Developer experience. So how are developers using this? Well, when you're building serverless technologies, you want to use a serverless CI/CD system as much as possible, for sure. AWS offers a set of tools called AWS Developer Tools that can enable standard CI/CD practices. I'm not going to cover them; they're very standard. What I'm going to add on top is a serverless framework. So in this case, we'll be using Terraform to manage our infrastructure as code for some systems, and then we recommend using the serverless framework for the Lambda functions. Serverless framework, which is very keen to Terraform for Lambda functions, enables this type of processing and allows you to do native deployment on AWS of Lambda functions and the connected services. And you can do even advanced things. You can do canary deployments and gradual traffic rollout. The CI/CD systems on AWS also support manual approvals, which are often a requirement for banks, for regulated industries. One last point on CI/CD experiences is testing and debugging serverless. Testing and debugging serverless is another key point. So how do we test Lambda functions? This is where I think the industry is lagging behind the most. We are not as good or as quick at doing unit tests for Lambda functions as we are of Maven systems, Java-based systems, or we have standard systems in either containers or VMs. In our case, we recommend using something like LocalStack. LocalStack allows you to have your small DynamoDB on your machine and doing your integration testing with DynamoDB on the machine. This enables you to avoiding having to go to AWS all the time, so avoiding to check this. And testing as well, making ample use of AWS X-Ray as well as CloudWatch, especially X-Ray, which is used for distributed tracing, as we will see in a moment. Okay. Perfect. So we're talking about performances now. So performances are key point on our system. So we're not discovering now that observability and monitoring are key for distributed systems as ours. But I think there's a shift in performances when it comes down to serverless and high-scale systems. So we're moving from numbers to percentages. In a case, this is pretty obvious if you want, but if you're processing 6 million transactions per minute, you get a 1 in a million event 6 times a minute. You get a 1 in 10 million event every minute. So things are happening all the time in this distributed system. When you have a lot of microservices, what you want to do is to look at, make ample use of AWS native services, stuff like Lambda Insights, stuff as function summaries, looking at the behavior of the Lambda functions, looking at how long each Lambda function does something, and looking at distributed tracing as well. How long in a request your system is taking to respond to the request, and where the time is spent into. Moving from number to percentage, as I say here in the slide, which is true, which is thinking about the fact that all your alerts, all your systems need to take into account this sheer variability of events that happen in a distributed system at all times. And you don't want to set up your alerts onto a number. We don't want to get alerted when we have 10 transactions failing. We want to be alerted when we have more than an X percentage of transactions failing, because transactions are failing all the time here. And then we're talking measuring. Now, this is I think this is an interesting slide because we're facing a problem here. One of the problems that we're facing is that if you think about the NFRs, the non-functional requirements, we want to make sure that we're processing our transactions from the mainframe onto cloud in less than 100 milliseconds. But how do you measure that? How do you make sure that your transactions are processed from the mainframe onto cloud in the same time frame? Making sure that it's 100 milliseconds, that the time frame is measured correctly. Because we have different clocks. We have different clocks. Now, having different clocks in all our VMs is a common problem. In data centers, all data centers will have a base clock, an NTP server that provides clock it provides NTP information for all the VMs in the system. But in this case, systems span multiple sites, one in cloud and one on premises. Also, we're using serverless, so we can really configure the NTP server that Lambda is using. Yes, I can bring up a Python function, I can bring up any function and say, okay, get data, get time from this, but I cannot tell Lambda use a specific NTP server. I can tell Lambda use the NTP server on premises. So measuring the offset is a tricky thing, because if you're expecting your system to process transactions in 50 or 100 milliseconds, well, if the offset between the clocks of the data center and Lambda is off by 50 milliseconds, then how do you know they're reliable, they're correct? So we have to synchronize clocks that we can't really synchronize because Lambda doesn't let us do it. So no guarantees are made, but we did some tests. We did some tests in this case, and tests are not conclusive, but basically say if you have a data center and AWS at 40 milliseconds, your clock offset is 10 milliseconds. What does it mean? It means that if information takes 40 milliseconds to get from data center onto the cloud, this results in a clock drift on average of 10 milliseconds. So you know where you stand, okay, with this measurements. This obviously will not go to 100 milliseconds of RTT larger offset as much. But you have some reference points to take into account if you have to measure events that span multiple distributed systems and multiple vantage points. And talking about measuring response time is key. And this is an example with X-Ray. You will see that X-Ray enables a series of optimization on the response time. X-Ray allows you to see exactly what the response time is of your distributed system. And you can see as well where you spend most of the time. This is really important for you to use. And then we have some series optimizations you can do on Java. I will refer you, I'm going to skip this slide briefly. I will refer you to a different talk that you can search online on YouTube under my name. Search my name, you will see we have a talk on this Java optimizations on Lambda. The takeaway is in this slide is to say, you can significantly optimize even a language that is not known to be very fast at boot up time as Java and get a very good performances. What will happen is that there are some performance samples, they're not the correct values, but just some samples that I just want to bring up. There's tell you what is happening with the system. So you see that there are orders of magnitude between the average and the P95 and the tail latency and the maximum latency. You see there's an order of magnitude between the time that the mainframe takes to kinesis on average and the time that a transaction takes from the mainframe to kinesis at a maximum time. This is not unusual. In a distributed system, you always want to look at a P90, P95 to see what the impact is. even if you think about this, even because the user to API gateway time gets even bigger, the difference between the average and the maximum. From the user to the API gateway, bigger variation. This sometimes is due to a VPN that may be in place that then is affected by the internet, or this is why we recommend Direct Connect. But the takeaway is, in a distributed system, you need to look at the tail latency, because the effect on tail latency can be significant for a significant chunk of your users. If you have 10 million users and you have 1% of those 10 million users that are experiencing 2 seconds, this is a problem because a significant percent of the users are being impacted. So doing performance optimizations in this case not only speaks to having to optimize Java. In our case, we have to optimize cloud as well. We have to make sure that we're using the correct features and options of Kinesis, the correct features and options of Lambda itself. Super important in this case, because performance impact can be done not only by choosing the right library or the right way of doing an action in Java the correct way, but a significant performance impact can be provided also triggered by some of the infrastructure components that surround your functions. And right before we end, in the last 10 minutes of our talk, or 5 minutes actually, before I'm going to have a 5 minutes Q&A at the end, we can talk about cloud operating model. So this is a bit of a tricky discussion, and I'm going to take you to think about something. When you're using serverless, what you're doing effectively is that you're pushing responsibility onto the cloud service provider. You're choosing ease of support onto something the cloud provider manages for you. But choosing serverless can be a bit of a challenge as well, because sometimes what you end up doing is that you end up using all these interesting tools, interesting systems that are designed to be used in a different way from the way in which your company is currently organized. Lambda function works very well for autonomous teams that can go and deploy and do what they want on their part of the stack. Lambda function works way less well when you have a team of backend developers that have to operate on the same Lambda functions. It was not designed for this. And so when you're thinking about building a system in cloud, what I wanted to say really in this last few minutes of the talk is that when you're thinking of building a system in cloud, you can choose architecture, you can choose you can think about your roadmap, you can think about the talent you have available, you can think about the developers, how skilled are they on these relatively new serverless technologies. But the point is that if your company does not have the right level of engineering maturity, if your company has never used serverless before, then it will be much harder for you to use serverless in one way or the other. If your company has never used Kubernetes before, even a different system before, a container system before, then it will be much harder for you to ensure that the operating model, the way in which your teams are structured, works in the right way for you. You need to think about this beforehand. When you're designing a new system, you need to think about what is the current level of engineering maturity and how are we going to operate this system. This speaks really true when you're thinking about microservices, when you're thinking about Lambda functions, because all these Lambda functions, all these microservices that you have available, they can be designed in different ways. Given a domain, you can create a lot of different aggregates you can define a lot of microservices on this. And people usually start thinking a lot, especially in small startups or in smaller companies, start thinking about a lot how we're going to define our microservices, which is a very important question. How we're going to break down our monolith if I'm moving a monolith to AWS to microservices. But doing this and choosing how to break up microservices is only a part of the problem, because the other part of the problem is who's going to run these microservices, especially in large enterprises. They have been running systems for the past 20 years. They have been running systems. They know they have established policies and processes. And changing those processes can be a significant hurdle. So what I would recommend doing is to think about this. think about the fact that changing the process is a hurdle. And when defining how to break down your monolith or how to design a new system with microservices, think about who is going to operate this. Because if you know already that a specific part of the company will be in charge of credit card processing, then maybe it makes sense for you to just go on credit to create a microservice just for that, because you think about the way in which the company is operating. This is described as well in terms of Conway and inverse Conway maneuver, defining a system for the communication structures of the company or defining the communication structures of the company for the system you build. All I'm saying is, when building serverless, building the technologies, make a conscious choice, thinking about who's going to support your system when it comes down to system and cloud architecture. So this was my talk. I think we are on time for the Q&A section, if I'm not wrong.
Thank you, Federico, for all your insights. Very interesting topic to talk about. Also, I'm myself, I'm a little bit biased and excited about doing serverless, but it's not the silver bullet for everything, right? You have mentioned it at the end of your talk about talking a little bit about the monolith, and I'm curious, what are your thoughts about just using a monolith nowadays?
I think there's space. I mean, I don't think people should go religious on this. I don't think people should just go, oh, we're never going to build a monolith. We're just going to go serverless for this. I think there's a space for having a simplified implementation when you have a simplified team. So if you're starting with something and you're not sure whether your idea will prove right or wrong, then you probably don't need to create 10 microservices and spend a lot of time deciding how to break microservices. Just build a monolith, do your test, and then throw it away at the end. That's easy. If you know that it won't scale, but if you know that you won't need to scale it, why the complexity? So there's definitely space for a monolith, even as a function of the company. So if you're working with a company that you know will be resistant to change, if you know that you have a company that is going to build a system that will not require significant scale, that will be operated throughout his life by one team only, maybe creating 20 microservices that are supported by one team, and it will always and only be supported by one team, perhaps it's just more complex than just building a system as we always been building systems.
So it's also about team topologies in the end.
Definitely, 100%. This is also one of my my core ideas in life, is where I really believe. I believe that building a system, building a cloud architecture is not only a function of technology, it's a function of the operating model and how a company operates and how a company wants to operate. I think that a lot of times enterprise architects throughout the years, in my experience in different companies, they are really focused on the technology, the trade-off of technology. They're focused on, oh, we're just going to choose one system or the other because one is faster, because the other is more reliable, the other is more correct, but in reality, enterprise architects in 2021, when they're dealing with high-level managed services, they need to think about as well how we're going to operate this, making a trade-off that goes beyond the technology, and goes into the company structure realm, talking with their teams, how are we going to release data here? Who is going to do this in a way that then you're good with that and you're comfortable?
And Federico, we have a question by Martin, and his question is, how do you deal with the question of data security and reluctancy of moving data offsite to cloud? It's maybe not only data security, we can add to that another one, anonymizing data, sensitive data, and of course, the GDPR things.
Okay. So this is a very complex question. I think there's a significant education that can be done, it can be performed. I think that sometimes, so a number of things are happening in this. I think that definitely helping the education, especially to your compliance function, and bringing the compliance function with you on the journey is really important. I think a transformation, especially in this case, should be driven by the business, saying this brings business value, and having the business mandate then allows you to perform transformation that you want. You need to experience some pain there. I think that in 2021, at least in my experience in the companies that we work with, and I've worked and continuous work with enterprises all over Europe, this is not 2011. So there's not a compliance function anymore that says no to cloud in general, that says, oh, cloud is not secure. They don't say that anymore. They say, oh, we have some complex technical requirements that cannot be easily implemented in a cloud native way. Tokenization, data masking, all the questions referring to. I think that there's an argument there to start working with the compliance team and doing a lot of educational workshops that help them understanding how data is secure by a lot of other banks, and then adapts their requirements as well. This is really important. So what I've seen sometimes happening is that there's a form of antagonism, a form of discussions between engineering and compliance, whatever. I think, again, trying to get together and building education on all this is really important.
Federico, we have other questions open, but unfortunately we don't have enough time for that. Are you around for the questions?
Of course, of course.
We can just ping you with through the social channels, right?
Yeah, of course. Definitely, you can write me in the chat. I'll be happy to chat. Or also, you can reach out to me on LinkedIn. Just add me on LinkedIn, and I'm more than happy to have a chat.
Thank you. And one last reminder to the audience, don't forget asking questions, and you will get a free ebook when you post the most questions from our media sponsor Pact. Thank you so far for attending. Many thanks, Federico, for your great session. See you all.
Thank you. Have a good day.